we're going to take a look at two last ways that we can go through and do some sort of numerical differentiation. And the first way that we're going to look at is we're going to take a look at how we can utilize MATLAB to use interpolations to be able to find approximations for our derivatives. Now, we saw in the last few sections that we could do polynomial fitting, right? We saw a least squares line, and then we saw, if possible, a polynomial interpolation for smaller sets of data that would pass through the exact points. So let's say for some reason we knew a function, all right? So let's say we have this function 3 cos of 2x, and let's say we want to find the numerical derivatives of that function at a few points. And we certainly go ahead and plug in like 0, pi 6, pi 4ths, and pi 3rds and get these values very easily, right? But we don't know what would happen to the derivative at values like pi 5ths and pi 12ths. So let's create a third degree polynomial because we have 4 points. And then we're going to plot the original function and the polynomial interpolation on the same graph. Then we're going to get the exact values for the derivative of 3 cos 2x at those 2 points, right? We're going to get approximate values by using the third degree polynomial and finding the derivative of that third degree polynomial. We're going to find the percent error. And then finally, we are going to create a table for this. All right. So really, we're finding the derivatives of the polynomial function. And we know polynomials are much easier to work with than trigonometric, other sorts of transcendentals. All right. So let's start out by defining a couple sims. So we'll say x, y, and f. And I'll say f1 as well. Actually, I'll call it f3 because it'll be a third degree polynomial, all right? And let's say the original function x is 3 times the cosine of, I think we said 2x. All right, let me just verify that just so that way I'm not doing the whole problem with the wrong value. And then now we have to store these into an array before we can get the poly function. So we have x, and let me just call this x1 is going to be equal to 0, pi over 6, pi over 4, and pi over 3. And the outputs for that, which is going to be y1, is going to be 3. And if we plug pi 6 in, that's going to be 3 over 2. And if we plug in, let me make sure these were the right values. All right, so we had 0, pi 6, pi 4ths, and pi 3rds, right? Okay. And so at pi 4ths, we have 0. And at pi 3rds, which would be cos of 2 pi 3rds, it's going to be negative 3/2. And we're going to get a polyfit for this. So let's call f3 to be equal to our polyfit. Well, actually, let's call p equal to that. Because remember, polyfit gives us an array of coefficients. So we're going to polyfit x1, y1, and we're going to get a third degree polynomial out of that. And then finally, f3 is going to be equal to p1 times x cubed plus p2 times x squared plus p3 times x, and then plus p4. All right. Now, we're going to plot both of those on the same curve. All right. And let me make sure there was nothing else that we had to plot. All right. So we're just going to plot, and we're not asked to plot these points on there. So, oh, the given points are expected to be plotted. Okay. So I'm just going to do an easy plot. So I'm going to easy plot. First of all, let's just easy plot f. And now let's hold and let's do an easy plot of f3. Right. And I think there was a range of values. Let me make sure there wasn't a range of values for this. No, it just said to go ahead and plot it. So we'll just go ahead and plot it. And then if I need to narrow it down, I'll narrow down the window. All right, so I'm going to easy plot f3. I need to hold on here. And then I'm also going to plot x1, comma, y1 as points. All right, and we'll hold off. All right, so let's see what we get out of this. Hopefully something nice. And we're really hoping that the polynomial function looks at least somewhat decent, and it does, okay, right around here, which makes sense because remember, it should only be good for 0 to pi thirds, all right? So this is pretty good. So I'm going to resize the window a little bit, all right? I'm just going to make this from, let's say from 0 to, since pi thirds is roughly about 1, let's just go ahead and let's just say that we're going to have an easy plot, let's say from negative 0.5 to 1.5. All right. And then I'll also plot this guy the same. All right. So let's get a new window and plot it. And there we go. Okay. And remember, we only care about from here to here, really. Now, notice how close it is after you start getting past this point. Like the two lines or the two curves are almost overlapping. Right here, there's a little bit of error. All right, but not too much. It's not too awful. All right. So we've gone through, and what have we done so far? We have done the polyfit, which we have. We've plotted the original functions. Let's get the exact values. Okay. So we're going to say, I'm going to say actual PI5 is going to be equal to, we're going to need the derivative. So let's find derivative is equal to diff of f with respect to x. And actual PI5 is going to be equal to, when we substitute into our derivative for x, and we're going to substitute pi fifths. And I'm going to do the same thing, but I'm going to call it actual pi 12. And I'm just going to say pi 12ths. All right, so those are our actual values. And it hasn't asked us to print it to the screen yet, I believe. All right, we're going to approximate the values of the third degree polynomial. Okay, so I'm going to call this estimated pi 5. And that's going to be equal to, so let's find, I'm going to call this e deriv, the estimated derivative. And that's going to be equal to diff of f3 with respect to x. All right, so that should be our derivative. And I'm going to say I'm going to substitute into the e deriv. So that's the substitution into the estimate of the derivative. The old value is x. The new value is going to be pi over 5. And just like we did before, copy and paste. And I'm just going to call this 12. And this is our 12. Okay, so we just took the derivative of the polynomial function. So now we have our actual, we have our estimate, and now we need some errors. So let's call this, I'm going to call this error pi 5 is going to be equal to absolute of our actual pi 5 minus, or I'm sorry, the estimate pi 5 minus the actual pi 5. And we're going to divide that by actual pi 5. All right. And I guess I should use an absolute value just in case, because I don't know what's going to go on there, and multiply it by 100 to get the percent error. And let's do the same thing for the 12. All right. So I'm just going to change all these to 12s, make it nice and easy for us. One of my computer science teachers would be really happy. These are good programming practices. Now, finally, we're going to go ahead and spit out the table for this. All right, so, and by the way, this is, so far we have found the exact values, we have gotten the approximate values, we've computed the percent error, and now we're going to go ahead and print out the table. All right, so we're going to have our point, and we are going to have the actual value, I guess. So we're going to have exact approximated percent error. Okay, so exact I guess we should say actual, because it probably won't be the exact. And then we're going to have the estimated. And then we're going to have the percent error. All right. All right. Now I'm going to do this in 2 lines. So we're going to have an f print f. And first of all, I'm going to print out our first point is pi fifths. And then we have a percent f for the actual. We have another percent f for the estimate. And then we finally have another percent f for the error. And our parameters are going to be our actual pi 5. And then we're going to have our estimate pi 5. And then we're going to have our error pi 5. All right. And then we can just cut and paste this. And we're going to change all the 5s to 12s. All right. Now, we should have some reasonably good estimates. All right. So let's see what we get out of this, if anything. All right. So, and let me go ahead and fix the spacing just a little bit. So this is going to be bumped over a little bit. This is going to be bumped over a little bit. And I'll just bump that over a little bit. And let's see. All right. So it looks like that the pi 5 is a really good approximation using the polynomial interpolation. The pi 12 is reasonably good. All right. We get about 3% error, 3.5% error, 3.45. And that's because if you look at the graph, remember that there was some space in here. All right. In fact, if we were to graph it from 0 to 0.5 instead of 0 to or negative 0.5 to 1.5, we'd probably see the disparity even more. All right. So let's just go ahead and do that just to illustrate. Because remember, pi 12 is pretty close to 0. All right, so we can see like right here, like pi 12 is, about a quarter or something like that. We start seeing that, yeah, there is going to be a difference, okay? But when we start getting to the pi fifths, okay, remember that's going to be 3.14 over 5, so that's like 0.6. So remember, if I was to do a really rough estimate of pi 12ths, that would be 3/4, okay, or 0.25. All right, and notice at 0.25, yeah, there's going to be a gap here. All right, but if we go back to the original graph, I'm just going to make this 1. And I'll make it 1.5. I'll make this 1.5 just to show for our graph. All right, now notice like right here around again, we had pi 6, so that would be 3. Or pi fifths, so that's 3/5 or 0.6. I mean, right here, we're almost in like the perfect zone of the overlap basically between 0.5 and 1 is a really good zone that we're in. So that's why we're getting like this little bit more error here, where there's almost 0 error at this point. So pretty cool that we can use polynomial interpolation to be able to help us with our derivatives. All right, and remember, there are other ways to do polynomial interpolation other than the polyfit function. I just use the polyfit out of convenience. But remember, we had Lagrange interpolations, and then we also had Newton interpolating polynomials. So we could kind of couple all of that if we really wanted to together. All right. So every time that we've done any sort of derivative estimation or numerical differentiation, we've had a function. But what happens if we just have a set of values? How do we start finding the derivatives of that set of values, and what does that represent? Okay, so that's going to be in the final video in this section, is if we just have ordered pairs, how do we go through and try to find some derivatives numerically of that stuff?